identity is an equation that is true for, I'm going to say, all values of the variable, excluding those that make the expression undefined. So for instance, a trig identity would be something like tan x is equal to sine x divided by cosine x, because it's true for all values of x except where, of course, x equals 0. Why? Where x equals 0. Yeah, because that would make the bottom or the denominator 0, and that would make it undefined because you're not supposed to divide by 0, right? And of course, then that means the non-permissible values is wherever cos is 0, which is, you know, pi over 2 and 3 pi over 2 in every spot in that domain. And this should be k is an element of integers, of course. It doesn't like it with my typing, I guess. Okay, so then we're going to graph y equals negative sine x. How do you do that? Y equals negative sine x. What's the sine graph that got? Reflected. So instead of taking your median and going to your max, we're going our median and going to our minimum. So it'll be like this. Okay, yeah. Okay, so I need to put a scale though. So that would be a height of 1. That would be a minimum of negative 1. And then we can put 2 pi here, yes? And pi here. You don't even have to put that much. The reason I put pi is, well, maybe in a second, I guess I need to put a negative pi here. We're going to take the sine graph and shift it to the left pi. So I'm going to take the sine graph that normally goes from the median up to a max. We're going to shift it to the left. And then what happens here? It's exactly the same. So what does that mean? What does that mean? Is this an identity? Is it true for all values of x? Yes. True for all values of x. So if you ever get down to trying to see if you've proven that they're the same, you need to, you can graph the two, and if they're the same graph, you know it's an identity. So before we can do that, there's so many fractions in this chapter 6 that we need to practice. So I want you to try example 1 ABCD before I actually do it. Do this in pencil because I think there'll be a few mistakes to be had here. Yes? Okay, so I saw a lot of good things on A. So this is the same thing as root 3 over 2 times 4 over 1. You need to see the cross-canceling going on. So 4 over 2 reduces to 2 over 1, right? You don't even need to put the 1s. So then you just get 2 root 3 as your final answer. The thing about fractions is your answers has to be one fraction. Okay, so then this one would be x plus 2 over x minus 1 times, then you flip this, right? So you get x minus 1 over 4x plus 1. These cross cancel and you're left with x plus 2 over 4x plus 1. Did anybody try to cancel some x's after that? Good. Otherwise you'd be killing some puppies there. Once you get really good at division, you can see, you don't have to show this, and you can just see you're going to cancel these, and you can cancel them right in there, right? Like you guys are in grade 12 pre-cal. You should be able to do stuff like that. You don't need to show all your steps. Just cancel, cancel, and then this gets flipped, right? Okay, this one, I saw brutal things happening here. This is the subtraction of two fractions. What's the rule when you're subtracting two fractions? They have to have a common denominator. What's the common denominator? X minus h plus 1 times x plus 1, yes? So that means this one is going to be x squared plus x. And then this is going to be minus 2 times that. So it's going to be minus 2x plus 2h minus 2. Yes? And then we have to combine these two. So my final answer would be x squared minus x plus 2h minus 2 all over x minus h. Oh, I forgot my plus 1. What the heck is going on there? We'll try that again. X minus h plus 1 times x plus 1. There's my final answer. Oh, yeah. You guys don't remember this from grade 11? You didn't have to multiply that out. Okay, so I saw people flipping these. No. This is a bracket on top divided by a bracket on the bottom. Do you know that? It's taking the whole top divided by the whole bottom. So what do I have to do first here? It's not division, so we're not flipping first. We need to do what? Huh? Common denominator. It's subtraction and addition. We got to add these things together. So what is my common denominator there on top? Sine theta, cos theta. And what does this one become? Cos theta. What does this one become? Minus. How about sine squared theta? Yeah? Okay, next one. Common denominator is those two multiplied together. So I'm going to write sine theta, cos theta instead of cos theta, sine theta. Why would I do that? Because then it will be the same as that one. Yes? So what does this one become? What does this first fraction become? Sine squared theta. What does this one become? Cos squared theta. Can you see when I now flip that these two will cancel? And what am I left with? Cos theta minus sine squared theta over sine squared theta plus cos squared theta. And that's your first identity on your sheet. Look at your formula sheet. What's sine squared theta plus cos squared theta equal to? 1. So this is really equal to cos theta minus sine squared theta. So where did this sine squared theta plus cos squared theta equals 1 come from? Do you remember your unit circle? And you had that nice little triangle there? And this coordinate was x comma y. What else was that coordinate? What? What do you guys? Yeah, it was also cos theta, comma sine theta, which means if I use Pythagorean theorem, this is cos theta, and this is sine theta, and this is equal to 1. Do you see how I'm getting sine squared theta plus cos squared theta equals 1? Oh yeah, there you go. Okay, so our reciprocal and quotient identities, who remembers what cosecant theta is equal to? 1 over sine theta. What's secant theta equal to? 1 over, cos theta. And what's cotangent theta equal to? Okay, so I'm going to put 1 over tan theta first. We're hardly ever, like 1% chance we're going to use that identity. What's tan theta equal to? Sine theta over cos theta. So using that analogy, what's cotangent theta equal to? It would be cos theta over sine theta. In all our proofs, we hardly ever use number 3. We always use number 5. And the reason why is a lot of our proofs, the whole point is to change everything to sines and cos. So when we start doing these proofs and you get stuck, have this hints for proving, because if you get stuck, part of this is problem solving. And if you just look, okay, so part of proofs is not just If you look at a proof and then you give up and you just wait for the next day, can you do number 5? You're never going to learn how to do proofs. You have to sit on it and kind of look at it and look at it and look at it until you figure out. And these hints will help you. So if you get stuck, go through the numbers and see if there's something you can do. Okay, so here's the first hint. Start with the more complicated side and try to reduce it to the simpler side. A lot of the times, the one side is way more complicated, and if you just add the two fractions together, it ends up being the other side. And you're saying, what are sides I'm talking about? We're trying to prove one side or the left side equals the other side to prove that they're true for all x's, or thetas, that they're the same, yeah. Number 2, if you get stuck, try working on each side separately. That's a legit way of proving. A lot of people back old school way is you could only start at one side and finish that side and had to equal the right side, say, or the other side. And we're a little bit lenient, so if you start on one side and you get stuck, start on the other side and keep going until they match, right? Okay. Third suggestion is switch everything to cos theta and sine theta. So for instance, tan, write it in terms of sine over cosine, right? Cotangent, cosecant, all those. Look for a common denominator. A lot of the times, if you get a common denominator and add or subtract them together, they end up simplifying quite a bit. A lot of the times when people get stuck when they start proving, if they would just see, if they factor something out, you can cancel something. So always look for factoring, canceling, simplifying. So for instance, what could I factor out of this one? Yeah, GCF of cosec. So if I factor out a cosec, I'm left with sine squared x plus cos squared x. And we just learned 2 seconds ago, what is that equal to? 1. So that means this is just equal to cosec. So you look at this big complicated thing, but that simplifies just to be cosec, right? Okay, here's a mistake people might make. If you expand this, what do you get? Nobody wants to say because I premised it by saying most people will make a mistake. How many terms do I get when I expand it? 3, yes. This is a FOIL. So you get sine squared theta, and then outer I get minus a sine theta cos theta. Inner I get minus sine theta cos theta. So I get minus 2 sine theta cos theta. And then last I get plus cos squared theta. And do you remember this plus this equals 1. So that means this is equal to 1 minus 2 sine theta cos theta. And that's actually equal to something else as well. It's on your formula sheet, but we'll just leave it like that for right now. Another thing where people get stuck is they see something and there's nothing to simplify. Something as simple as this, they're like, I don't know what to do with it. Guess what? Multiply the conjugate. So what's the conjugate here? What's the conjugate? 1 plus cos x over 1 plus cos x. And so what do you get when you multiply those together? Well, on top, you get 1 plus cos x. And on the bottom, it's a FOIL. The whole point of the conjugate is what? When you FOIL it out, you get rid of the outer and the inner terms, the middle terms, right? So first you get 1. The outer and the inner will cancel each other. And then last you get minus cos squared x. And that's actually an identity. This right here. And you know what the identity is, actually. Yeah, watch this. if you have sine squared x plus cos squared x equals 1, and I move this over to the other side, what do I get? Sine squared x equals 1 minus cos squared x. And that's what this is. So this would simplify to be 1 plus cos x over sine squared x. Of course. Number 7 with 4 exclamation marks would be don't. No, you want to cancel. Don't introduce dividing. Don't introduce dividing, meaning don't try to divide both this fraction by 5 theta, sine theta or something. Why? Why? You were going to eliminate one possible solution. Plus, there's a huge thing when you introduce dividing. If you're dividing by a variable, you don't know what the value is. And 99% of the time, that value is 0. And that means you're dividing by 0 then, which is a big no-no in math, yes? And this is something I know I said before, oh, you could skip steps and stuff like that. In proving, you have to show every single step. If you think it, you have to write it. Otherwise, you could just say, oh, that side equals that side, I'm done. You have to actually show the whole entire process. Okay, so here's a little star. To prove an identity is valid, it must be shown that one side of the identity is equal to the other side, or that both sides are equal to the same expression. Here's even a little kicker on that too. If I have sine theta times cos theta on one side, and I have cos theta times sine theta on that side, although they are equal, I can't say they're proven equal until they look exactly the same. So the next step, you have to write it in the same order. Yes. Yes. A verification of a specific value shows that an identity is true for specific values of variable. It does not prove that an identity is true for all values. The only way you can prove it's true for all values is by doing some general value x. If you just substitute, say, pi over 2 in and see if it's true for pi over 2, that just means it's only true for pi over 2. Okay. So here's our first proof. It's exciting. So on the provincial exam, they give you this T-chart to organize your thoughts. I like the process of the T-chart because then you don't write equal sign. And what a lot of people start doing is they start putting equal sign like everywhere, and it's just a mess. So first step is, this is my left side I got to write in. So secant theta, 1 plus cos theta, and then 1 plus secant theta on the right side. So the first step is, again, you have to write every step, right? Okay, no equal sign. We're trying to prove that it's equal. So some textbooks, they use 3 lines. Some textbooks have an equal sign with a question mark. You're trying to prove that it's equal. And then, of course, there's always a question from students. Have they ever given you something to prove that's not equal? No. No. Or they'll introduce it to say, this proof isn't true. Find a value that it's not true for. Something like that. But they would never get you to prove it because it's like spinning your wheels for nothing. Huh? So these proofs are 3, 4, and 5 mark questions on the exam, and you have to show every step. So every little step that you're showing, you gain a half mark here, a half mark there, a half mark there, right? Nothing. It's the process. It's the journey, not the end result. Okay. So I guess what I'm trying to say also, because the journey is worth all the marks, don't ever leave it blank. Changing, for instance, secant into 1 over cos theta, that's a half mark you just gain. If you would have just, even if you can't do anything else, that would have been a half mark. Okay, so remember our hints there? What was our hint say? Start with the more complicated side. What's your, it's opinionated which one's more complicated, but I think with brackets and stuff, this shows to be more complicated, yes? Okay, so start with the more complicated side. One of the hints also is write everything in terms of sine theta and cos theta. So the secant theta, although it's on both sides, it's harder to prove that they're equal to each other if you leave the secant theta in there, because you have a cos theta already. So it's just way easier if you just change it all to sine and cosine. So what's secant theta equal to? 1 over cos theta. And then this is times by 1 plus cos theta. Yes? Okay. So what should we do now? Huh? Yeah, it actually times it. Perform the operation that it says. So we're going to multiply this into both. So what do we get? Remember, this is over 1, yes? So what do we get when we multiply that? 1 plus cos theta over cos theta. And you might say, I don't know what else to do there. Or you could say, oh, I can see what I can do there. Can anybody see what they can do? Go like this. Bam, it's equal to 1? Yeah. You just killed a puppy. Yeah, so no, you can't do that. It has to be common to both. This is a binomial and this is a monomial. You can't cancel a binomial. It's attached to the 1 there. So I would say maybe you can leave it. Here's where your friend will be doing some proof different than you, right, at the end. So you might want to say, well, it's an opinion, right? So that a lot of the answers in the back of the book, they're not even there. Because there's an infinite way to prove something. So I can see what you can do here, but maybe you can't. So then you stop and you go to the right side. Whereas somebody might just keep on continuing here. And I'll show you in a second what you could have done. So anyways, secant theta on this side, we could, what? Change to cos. So 1 plus 1 over cos theta. Looks very similar to the left side, but it's not quite there yet, hey? So what do you think we should do next? Common denominator and put them together. What's the common denominator? Cos theta. I highly advise trying to do this in one step, right? Because a lot of the times it's just two fractions that you're adding together. And so what would you have to multiply 1 by to make it over cos? Cos theta. And this is already 1 over cos theta. So now are they the same? Yeah, I just said you have to, the next step, either rewrite the left side or rewrite the right side. You can't leave it like this and say they're the same. So 1 plus cos theta over, see in your head you're like, oh, they're kind of the same, so they're the same. Remember, anything you think in your head you got to write down. So write this down. Now they're exactly the same. And the end of the proof, you're supposed to say, therefore, the left-hand side equals the right-hand side. And you're supposed to really put identity proven, or the Latin thing, QED. Have you ever heard of QED? I have a t-shirt actually that says QED. It's quad estro demonstratum, which means that you prove that these are true. Anyways, so you learn QED. You don't have to write that, but I'm just teaching you some higher level stuff. When you get to calculus, a lot of the proofs that they show in the textbook, they'll say QED at the end of it. So, or sometimes they just put a little box. I don't know why the box means that, but anyways. Okay, it says here for each identity below, verify for theta equals 30 degrees, then prove the identity. Determine all non-permissible values. So I didn't do any of that. I went directly to the proof because I could just tell you wanted to do that, right? So anyways. Okay, so we're going to go to the left-hand side, and we're going to sub in theta equals 30 degrees. Okay, so the left-hand side is secant of 30 degrees times 1 plus cos of 30 degrees. So what is secant of 30 degrees? Two over root 3, very good. And what is cos of 30 degrees? Root 3 over 2, so it's going to be 1 plus root 3 over 2. Oh, could you get a nicer one? Anyways, what can we do here? Multiply it in, yes? So what do we get when we multiply that in? 2 over root 3 plus? Do you see they cancel when you multiply it? So it's going to be plus 1. Okay, so we're going to leave that like that and see where we get. The right-hand side is 1 plus secant of 30 degrees. So what is that? 1 plus 2 over root 3, which is 2 root 3 plus 1, right? So that means it's true for theta equals 30 degrees. The second thing they asked me to do is we need to or maybe it's the third thing, is to determine all non-permissible values for theta. So any non-permissible occurs when, what? We learned this last semester in your rational unit. Equals 0. Whatever makes the denominator equal to 0, which makes it undefined, right? So whatever makes something undefined, and essentially in our math right now, because we're dealing with a lot of fractions, it's usually the denominator equals 0. If we ever get into square roots, what would make it undefined? Yeah, a negative inside the radical, right? Okay, so there's other ways to make things undefined, right? It's just in fractions, the denominator equals to 0. So here's the thing. Anywhere you, and that's why I like actually showing the proof, anywhere you see that you have the potential to have a denominator, that is the potential to have an undefined. So, does anybody see a denominator there? Cos theta. There's a bunch of denominators where cos theta occurs. So that means cos theta cannot equal 0, which means theta cannot equal, where is cos theta equal to 0? Then 90 and 270. So how do I write that in degrees? So 90 well, it's just because they started in degrees, I'm going to keep it. So if we have that spot and that spot, how do I say 90 plus? So not pi, 180k, yeah, plus 180 degrees k, where k is an element of the reals. Yes. So there is my undefined, or my non-permissible. There's my solving, and there's that. Okay. Right. Because it doesn't have a restriction on the domain, right? It doesn't say it's just one revolution. I don't know why that is. That's a big mistake. Thank you for correcting me. K is an element of the integers. Oh, you can put fancy brackets around there. Okay, you guys want to try the next one? Oh, yeah. Oh, yeah. Okay, first step, write it in the thing. 1 minus tan theta. The next one is cotangent theta minus 1 over cotangent theta. If you're good at chess, because you can see like 5 plays ahead of you, you'll be good at proofs because it's the same thing. You have to see where you're going so that you can get to the end result. Like if you just look at the next step, you might not get it. So for instance, it's up to you whether you change all your tans and cotangents to sines and cosines. But if you had tan on one side and cotangent on the other side, you could switch it to tans, right? Yeah. So anyways, which one's the more complicated side? The right side, definitely. So, you know, some people want to just go cancel, right? Kill the dog, right? Puppy? Not a good thing. You guys know what I'm talking about there, right? Okay, good. I don't want to say I love dogs here, but I have that puppy meme, right? So, right? You guys know what I'm talking about? Okay, so we're going to start with the right side because it's more complicated. Does anybody know what we should do? You could. You could. There's a much really easier thing to do. You can actually divide this like it says here. Divide to both of them.
So you get 1 minus 1 over.
Then you get 1 minus 1 over cotangent, which is what? 1 minus tan theta. Done. But if you didn't see that and you change them all to sine and cosine, it's not that you're actually wrong. It just takes a lot more steps. Yes. So, for instance, here, if I said, oh, I didn't see that at all, and you started changing it into sine and cosines, like I said, it would have taken, you don't have to erase yours. It's probably right, as long as you get the left and the right-hand side. It's just way more steps. That's what I'm saying. You might do your homework and do it a certain way, and then your twin brother will do it a different way, and it doesn't mean one's right over the other. You're probably both right. And how do we check if we're right? I divided cotangent into cotangent, I got 1, and I divided cotangent into 1 and just left it as 1 over cotangent, right? Honestly, you guys learned this little procedure in grade 9. It's just a little more complicated with the cotangent. In grade 9, you learned 10x minus 2 divided by 2. You learned that you can divide both of them by 2. That's the same thing there, right? How do you what? Okay, so anyways, we need to prove it for 30 degrees. So, left-hand side, 1 minus tan of 30 degrees. What's 30 degrees for tan? Yeah, 1 minus 1 over root 3. I think I might just leave that like that for right now to see how the right-hand side treats me. So, right-hand side is cotangent of 30 degrees minus 1 over cotangent of 30 degrees. What's cotangent of 30 degrees? Root 3 minus 1 over root 3. So you can make the left-hand side, or if you just saw my trick I just did before, you can divide both of these by root 3 and you get 1 minus 1 over root 3. Therefore, true for theta equals 30 degrees. Now, technically, in a question, you're not supposed to leave things as two fractions. It's supposed to be one value, but when we're trying to verify that it's true, you're just looking to see if it's like they're the same. Okay, so where is there a potential for non-permissibles? So when cotangent equals 0, so cotangent theta cannot equal 0. Any other ones? Okay, so here's the thing. Although tan is not written as a denominator, it really does have undefined areas, right? So where would tan be undefined? Well, you know it's the y-axis. But because tan is sine divided by cosine, it's where cos theta equals 0. And I don't know if you might realize where cotangent is undefined, or you might write it as it's where sine theta equals 0. So does everybody see? These are pretty much the same thing. This and that, and this and that, because that's what makes it undefined, right? So we're not done yet. We have to say where the non-permissible values are. So theta cannot equal what? What? Theta cannot equal what? Wherever sine and cosine are 0. So where's that? Every 90 degrees. So how do we write that? Yes. 90 degrees plus 90 degrees k. Very good, where k is an element of the integers. And if you don't get that, you could just write, 0 plus 180. Okay, so 90 plus 90k. Anyways, let's try the next one. Do you want to try these yourself? Not yet. You're not ready for it, eh? Okay. Cotangent theta over cosecant theta equals cos theta. So, pretty obvious which side is the more complicated side, right? The right side. That's pretty, yeah, cos theta is pretty elementary. Okay, so what are we going to do here? If we know our end result is getting the right side cos theta, then what would we do here? Make them into sines and cosines. So what's cotangent equal to? Cos theta divided by sine theta. And here's a little trick. I always make my division sign like a thicker one because you might get lost in which one's the division when you have complex fractions. Cosecant theta is equal to 1 over sine theta. Does everybody see if I flip, these will cancel? And then I'm just equal to cos theta. It was a pretty easy proof, actually. Okay, and then it also asks for the non-permissibles. So, theta cannot equal what? A lot of the times the proofs are, the proofs say, prove the identity is true for all permissible values of theta, which means then you don't have to actually find the non-permissible values. Okay, so does everybody see? It's where sine theta is 0, right? So where's that? So because I'm actually rewriting it, it's where cosecant theta equals 0 too. So yes, you're right. So maybe we want to write this a little bit. The problem is cosecant theta equals 0. Okay, anyways, I'm running out of room here, so maybe I'll just, so it's where sine theta cannot equal 0 and cosecant theta cannot equal 0. Does everybody understand why they both can't equal 0? Because right here we have a denominator, and then right here we have a denominator. Yes? Okay, so non-permissible values is where theta cannot equal, not sine theta or cosecant theta. So where's sine theta equal to 0? Zero, pi, 2 pi, those, yeah. And where's cosecant theta equal to 0? Cosecant is sine, so all the way around. So just to give you a visual here, right? Does everybody see sine theta? That's your y, right? So that would be 0, pi, 2 pi. Do you get that part? Okay, so now how does cosecant theta get 0? I hear people giving me values, but think about this for a second. How does cosecant theta give you zeros? What do you mean undefined? There's not a value for undefined there, right? How are you getting values for... If you recall what the graph of this looks like, you'll be able to tell me that there's no spot where it's going to be 0. But if you think about this logically, if cosecant is equal to 1 over sine, how do you get a 1 divided by something give you 0? unless you're taking 0 and dividing by something. Do you see what I'm saying? You can't. So this actually doesn't attribute to any non-permissible values. And again, if you remember what the graph of cosecant looks like this. Remember? It never touches the x-axis. Do you remember us doing a graph like that?
Yes.
I think we might have done secant, but it's the same graph, just shifted, right? Okay, so anyways, where is sine 0? We said 0, pi, 2 pi. So that is k pi, where k is an element of integers. Okay, next proof. Cos theta. 1 plus cos theta over 1 plus secant theta. Very obvious. Which one's the more complicated side? Yes? So, what are we going to do on the right side? Change it all to sines and cosines? Sure. 1 plus cos theta divided by, again, I make this thicker just so I don't lose my, which ones are dividing, 1 plus 1 over cos theta. You see why I got you to practice some of your fraction skills first? It's going to get crazy like that all the time. So in order to divide, we have to do what first? Yeah, we need to actually put this into one thing there, right? So 1 plus cos theta. And what do we get on the bottom there? Cos theta plus 1 over cos theta. Does everybody see that's what you would get? Okay, can you see a cancellation that can occur? Yeah? So what does that flip to be? Cos theta. Therefore, the left-hand side equals the right-hand side. Okay, so we need to do non-permissible values again. So where would non-permissible values be? Cos theta cannot equal 0. There's another one, though. This one right here. Secant theta cannot equal -1. Yes? Okay, so now my non-permissible values are theta cannot equal. So where is cos 0? 90 to 70. Let's do it in radians this time. So pi over 2 and 3 pi over 2 and everyone in that spot. So how do I write that? Plus k pi. Very good. And then secant -1. Secant -1. That would be where? What's -1? Cos. Where's cos -1? At pi. And pi plus what? Plus 2 pi. It's only where pi is, right? So 2k pi, right? Where k is an element of the integers. All right, we have one last proof here. Let's do this. Okay, cotangent x plus tan x, cosecant x times secant x. Do you notice how I stated it this time? I said prove for all permissible values of x. That means we don't actually have to state the non-permissibles this time. And that's how a lot of the times on the proof on the exam will be, unless they specifically want you to find the permissible value, non-permissible values. Which one's more complicated, a multiplication or an addition? Addition. Addition is complicated because? Yeah, well, usually it'll involve some fractions too, which you have to get common denominators and all that stuff, right? Okay, so what do you want to do on the left side? Change it, right? So don't put thetas now. This isn't x's. Otherwise, you'll lose a half mark for introducing a variable. Okay, so cos x over sine x plus sine x over cos x. What's my common denominator? Sine x cos x. That's a cos. What's the first numerator going to become? Cos squared x. What is the second denominator going to get? Sine squared x. And what is that equal to again? 1. So this is 1 over sine x cos x. So you might stop there, or you might recognize what that's equal to. Do you see ahead of the game, it could equal this if I separate them, right? Yes? Or what you could do is you could change this to sine and cosine and it'll get it like this. So it's up to you. This is why I'm saying your proofs will alter depending on what path you take. So which path do you want to take? Go on the right side now? Yeah, most people would go that way because they probably can't see it the other way. So cosecant is equal to 1 over sine x, and secant theta is equal to 1 over cos x. Do you see? This is what I was trying to say to do on the left side, is separate them like that. So anyways, when I multiply that together, what do I get? Yeah. Isn't it a good feeling when you get a proof to work? Yeah, but sometimes you get stuck. That's what I'm trying to say, right?